slideshow. All right, well, welcome to the pre-test day review for week 5. So last week we talked about isomers and everything, and this week we're going to talk about bromination, which is what you all covered last week. So, fun stuff. This is your first reaction y'all have done. So, very cool, very exciting preview of upcoming stuff. So from now on, towards the end of OChem, which is like forever, if we think about it, y'all will just be doing a lot of reactions. And so this is really fun, but this is also very different from most of the reactions y'all will work on. So, yeah, so the YouTube videos are still going. You can access them on the link. And yeah, we're recording, so FYI. So, let's go ahead and start with just dive straight into reactions. Y'all should have talked about it last week, I would hope, as a test. But, so, basically what we're doing is, I've got a couple structures, and we'll talk through how they go through the reaction. I'm doing it with Br2. So what does it mean if I have Br2? What kind of reaction?
Bromination.
Yes, bromination. We have a lot of different kinds of halogenations. We usually do bromination or chlorination. All of these I chose to do bromine, mainly because it kind of demonstrates selectivity a little better. Chlorine is a lot less selective than bromine, and so I like using bromine for these examples. For this reaction, there is a mechanism, which means that y'all need to figure out how the electrons flow and all that. That's very important. There's, in the future, some reactors where you don't need to know how it works. This one is one that you need to understand how it works. So, for halogenations, the big thing we're thinking about is radicals. And a radical is just one electron, right? So, if I had fluorine, these are called lone pairs. But if I have this is what I call a free radical. And free radicals is what we're talking about when we do halogenations. In halogenations, we're doing free radical reactions. Okay, so we say the following structures are reacted with bromine and light. So what's happening? Oh, that's not a pretty one. Okay. What's happening is I've got the arrow, I've got light, and Br2. Okay. So the first thing that happens is bromine is the thing that's getting hit by light. Very, very important. It's not this structure, that gets hit by light. It's the bromine. Okay? So what's happening is I have Br bonded to Br. Okay? That's what a bond looks like. I've got all my radicals, all my lone pairs around it. And this is a covalent bond, which means that I have one electron here and one electron here. Okay? Covalent bond, you're sharing 2 electrons between the 2 atoms. And what's going to happen is when light hits it, it's going to destabilize the bond, and what's going to happen is I get this. What that means is, first of all, notice on the arrow, do I have 1 pointy or 2 pointies off the arrow? 1, okay? So radical reactions, we always want to use 1 arrow. It's called a one-headed arrow because how many electrons are moving in a radical reaction?
A radical is 1 electron.
Yes, right?
So a radical reaction is 2.
A radical reaction is 1 electron, right? So the bromine takes 1 of these electrons, and the other bromine takes the other one. Does it make sense? So what I get is bromine with 1 electron, with 1 free radical. Okay? And now I'm going to bring in my other structure. So now I have, and this thing has multiple hydrogens, right? I have hydrogens everywhere. And what the bromine is going to do, it's going to abstract a hydrogen. Okay? So, in the hydrogen, I also have bonds, right? And each of these covalent bonds also have 2 electrons. What's going to happen is, bromine is going to donate its electron to a bond, and so is hydrogen. Hydrogen is also going to donate one of its electrons to the bond, and that other electron is going to end up on the carbon. Okay? So now what's going to happen is I get bromine with hydrogen, and I get my propane, no, this is my butane, with 1 electron. I have a radical here. Just like that.
Did it matter what hydrogen we did it with?
In a way, yes and no. So it matters in the sense that we want the most stable radical. And we'll talk about this more. Let's go through the entire thing and I'll explain like why it matters, where it matters, and all that. Okay, so I've got this, and I'm going to keep going. Because guess what? I've got another radical that's free floating. We're going to use green. Okay, so this radical, remember I only used 1, so this other radical is going to come over here. And, yeah, no, that's not really pretty. Okay. This radical is going to fly over here. Remember, I'm doing this where I have more than 1 bromine, so we just have lots of bromine radicals flying around. Here I'm saying that this one is the one that's getting pulled, but in reality it doesn't matter which one gets pulled. But I have this other bromine, right? And it also has a radical. This is what I call the Christmas tree bromine. It's green and red apparently. But now what's going to happen is the radical then reacts with the propane. So, butane. So this radical is going to come in and make a bond and donate one of its radicals. And the carbon, because it's not happy with just a radical, is also going to donate its radical to make a bond. What I end up with is this. Basically what happens is I lose my hydrogen and I gain a bromine on that structure. So, does it matter where the bromine ends up? Yes, and we're going to talk more about ranking radical reactions, but basically I want the most stable radical possible. So, any questions on how radicals work? And what the most stable position for a radical is?
So you mean stable mean by the secondary, like 2 degree, 1 degree, that?
Yes, yes. So you would prefer to put a radical in the tertiary position, secondary, primary, like all that.
So the tertiary for bromine is more stable than secondary and the least is primary?
Yes, and all that, yes. Questions about how this works?
So what, because there's 2 bromines, right? So the second one, that radical reacted for bromine.
Yes.
6 and off. Okay.
Now, usually, if I'm doing this in a model, right, I'm going to have lots of bromines flying around, so not necessarily the exact same bromine, but that's the general gist of how that works. Other questions, comments on how this works? Alright, cool. So, I'm not going to go through the entire propagation of how the bromine breaks apart. All we're going to do is when we think about this, we're going to decide what's the best position for my radical, and we're going to go from there. Alright? So, this one is very similar. So I also have a butane, but this time I have an alkene. So I'm going to first draw out basic reaction. Okay. Light and Br2. Okay. So I've got this structure. Where would I abstract my hydrogen?
This one?
Which one?
The corner.
This one?
No,
This one? This one?
the fourth one.
This
The
one?
corner.
This one? Does it matter for 1 or 4?
I don't know. We studied the allelic, which forms right next to the double bond. So I thought maybe that would be the one.
That is correct. We want to prefer the allylic position. So let's go way backwards to when we talked about acid and bases. Why does resonance help with acids and bases? Why does it make an acid more stable?
It's additional bonds, isn't it? So it just kind of reinforces the structure. I don't know.
Yes, so what happens is resonance allows me to spread that extra electron density over a greater area. Okay? So when I talk about radicals, I'm actually lacking electrons, but it works in the same way. When I lack electrons, I want to spread that lack of electrons over a greater area. So with radicals, it's more stable if I can get it into a place where I can resonate. So if I abstract 1 or 4, in this case, it doesn't matter which one I abstract because it's the same. It's the same structure. It's symmetrical, right? So it doesn't matter 1 or 4. I'm going to abstract 4 just to make it, I don't know, easy for me. It doesn't really matter. Okay, so I've got my bromine here, and I've got my free radical. What I'm going to do is I'm going to come in, make a bond. I have 2 electrons with hydrogen. The hydrogen's going to donate one of its the hydrogen carbon bond is going to donate one of its electrons. The other one's going to end up on the carbon. So what I get is this. Okay. So this is a resonance structure. So I can resonate. Okay. Between these 2 resonance structures, which position is preferred? All right, so what kind of structure is this? This is going to be primary resonating. Okay? And this one's going to be secondary resonating. Which one is the preferred position for a radical? Do I want to be primary or secondary? Secondary, okay. This is going to be preferred. Okay. So I'm going to choose the secondary one as the one I work with. And I just put my bromine here. That's it. Questions, comments?
You kind of like move that double bond to that side.
Because it's resonating. Because I can resonate. That's why. It's more preferred.
So what would be the rate limiting step?
The rate limiting step I'll get into when we go to question 2. So it'll make sense when we go to question 2.
So that end is a product, and that would be the mechanism between the beginning and the end, right?
Yes.
Okay. Okay, that makes sense.
Alright. So, actually, do y'all want to do C, D, and E, or do y'all want to go to 2 and then 3, 4, 5, and then come back to C, if y'all want, if we have time. It's up to y'all. One more? Okay, perfect. Do y'all want to do a specific one, or do you guys just want to do C?
So E will have 2.
E is 2, so you have to pick.
Can we do E?
Y'all want to do E? Okay.
Yeah.
All right, y'all want to do the most complicated one. Okay. All right. So E, same thing. Light, Br2. Okay. So let's talk about our options. Okay. So let's do the first one in purple. No, purple. I want purple. I'm going to say that I work with this bond as resonance. Okay. If I do that, I have this. This. Alright, so if I do that, I'm going to abstract this radical. This is where I'm going to put the radical. And I get resonance like this. Okay. So here I get a tertiary and then a primary.
So tertiary is much better.
Yes, but let's do the next one. So, the next one let's do in green. I'm going to take this radical with this double bond as resonating. If I do that, this is secondary, primary. So which one is preferred?
The tertiary and the secondary because of the stability.
Well, I can only pick one place to do my
So then
position.
tertiary.
Yes, so I would prefer to do it on the tertiary bond. On the double bond where the tertiary is. Does that make sense?
Even though if we have 2 double bonds, we don't have to draw it 2 times the bromination.
You're going to pick the most stable. If they say pick the most stable, you pick the most stable. The most stable is a tertiary resonating. Okay? So, that's going to be the most stable one, and I get this. And this is most preferred, tertiary, and primary versus secondary and primary. Does that make sense? Questions? Thoughts? Alright, perfect. Now let's go to 2. And this one, I just want y'all to think through reactions and how they work. Okay, so first of all, let's do the energy diagram for structure A. So I'm going to do my big energy diagram. Oh, that's not pretty. Hold on. The other one was pretty. It's not better, but you know. Okay, so the 2 top lumps are what we call the transition state, right? And so I have start, product, and what do we call this? Intermediate. Okay. So for here, I started out with this. Right? My intermediate was when I had my radical. My transition state, should I do this in a different color? I don't think, it's fine, okay. My transition state was when I was making the bond my other transition state was when I was making the bond with the other bromine. And my product was this. Okay, this is what I call start, product, and this equals transition state. Okay, so when A is changed to B, so structure B had a double bond. When A is changed to B, would that make my reaction go faster or slower? So I just drew out my energy diagram. Questions about energy diagram and how I did that, and what it means and all that.
It's two transition states because it went through two steps.
Yes, yes. Two transition states, two steps. The transition state is when electrons are moving.
So the B is the second, like the second half?
No. So what I'm saying is, if I changed the start material from this, if I changed it, from this to this, would it make it faster or slower?
It would make it slower because the second one is making at 1 degree. The B is making it at 1 degree and the first one is making it secondary.
Okay. However, am I making a more stable or less stable intermediate?
You change it to B, you make it into a less stable?
Does the double bond make it more or less stable? More stable. Okay. So I'm going from a less stable to a more stable. I'm making my intermediate more stable. Okay? If I'm making my intermediate more stable, will that lower or increase the energy here? The energy of the intermediate.
It would lower.
Lower it. The more stable I am, the lower my energy. If I lower my energy of my intermediate, it's going to lower or increase my transition state and my activation energy. If my transition state is more stable, will that lower or decrease? Will that increase or decrease my activation energy?
Well, would you need less energy if it's decreasing?
Decrease it. Decrease what?
The activation energy?
Activation energy?
Yes. So if I decrease my activation energy, would that increase or decrease my reaction rate?
Increase it.
Increase it. In other words, it goes faster. Does that make sense? How I got there? So just think through energy and time and how much energy you would need to make something work.
Is this the same as he was talking about bond disassociation energy?
Yeah.
Is that what this concept is?
Yes and no. So bond dissociation energy goes into this. So the more easily you are able to break your bond, the higher your reaction rate because you can go faster. So it's a similar concept, but I don't think it's this question per se.
Okay.
Wait, it might be. They're all very, very interrelated, that's all I'm going to say. So questions on A. How I did A.
So in the chlorination reaction, it won't matter if the A is changing to B because it's not selective, right?
Yes and no. So here, what I'm saying that if I change the reagent, would that increase or decrease the speed? If I just added a double bond, would my reaction be faster? So your question actually leads into the next question, right? So here, I'm not talking about the carbon-carbon product. I'm talking about the halogen. Okay. So if I change my halogen, what would change? So if I change my halogen from bromine to iodine, would that make it faster or slower?
Okay, so iodine is bigger than bromine. So what will we be looking at? Are we looking at the size? Are we looking at electronegativity?
There is a chart, but basically what happens is I have fluorine, bromine, iodine.
So it's small.
Okay, so iodine is extremely slow. In fact, it basically never happens in the idea that it's so slow we can't actually see it happening. So iodine would be far slower than bromine is. But if I change it to fluorine,
Speed.
it would speed up and you would probably die because it is very, very, very dangerous. Very fast. Explosively fast. Okay? So I did this so that we can think about speed. So the main ones that we work with are chlorine and bromine. Now, chlorine is less selective. And the reason why it's less selective is because it's faster. If I'm faster, I'm just going to go wherever I go. If I'm more selective, like bromine is, then I'm slower, and so I'm a little more picky. That's basically the concept.
So like fluorine's like barely selective, which is why
It's really fast. So, for example, between the secondary position and the primary position, the speed's about 50%. No, not the speed, the rate. So I have 50%. It's closer. It's like I think like 45, 55 between secondary and primary. Whereas with a bromine, it's like 97 and 3%, I think. So it's very, very, very different. And it's mainly because of speed. Speed has everything to do with how this reaction goes. Questions? Comments? Alright, so temperature. If I increase my temperature, will that speed up or slow down my reaction?
Speed.
Speed up, right? This is kinetics. More energy means faster. In fact, bromine generally is heated, and bromine is generally heated to speed it up. Chlorine doesn't need heat. So, and then if I decrease, it's going to decrease temperature, it's going to decrease. Pretty straightforward. Questions, comments?
So I'm just concerned, like if instead of the bromination, it's chlorination.
The same concept happens, right? The same concept would happen if I increase my temperature, so if I add heat, chlorination would be faster too. Yeah. Alright. You all kind of understand how the energy diagram works? Because for this, it's like, but this will make sense when we do other reactions, right? So we're using this as a model. We're using the energy diagram as a model for when we start doing different kinds of reactions.
So
And it kind of makes more sense.
real quick, this overall diagram is exothermic.
In this case, yes, because you're giving off energy.
Okay. So
Don't
that's
quote
how
me.
you do.
Don't quote me on it. Yes. And this is, okay, so
So is chlorination exothermic or endothermic?
I do not remember. I'll be honest. I think one of them is exothermic,
Yeah, I
one of them
know.
is
So that's
endo.
what I'm thinking.
Yeah.
Double check your notes. One is exo, one is endo.
One is-
I don't remember which one is which. However, most of the time we usually draw reactions like this. When I draw like a basic like template for what a energy diagram looks like, you usually start with a higher energy and end up with a lower energy. That's not always true. You can always do this, right? So if you need energy, but generally speaking, this is how we draw it, but it depends. So I know I drew this for a butane with a bromine. I'm not sure if it's accurate. This is just how halogenation usually works. I think there is a copy of this specific reaction in your notes, which I should. Yes, question.
It's actually, I think it's the question you had about the,
Rate limiting step?
The bond.
no, what you just say?
Rate limiting step?
Yeah.
Yes. Sorry, I completely forgot. Okay, so let's talk about rate limiting steps. So-
Oh, yeah,
Yeah.
yeah, that's what, yeah.
That's really ugly. Okay, hold on. Rate. Okay, so a rate limiting step is basically the highest point of my energy diagram. Okay? What that means is this is the step that takes the most energy. So if y'all look, here my energy of activation is highest. Which means it takes the most energy. So after I pass that energy of activation bump, everything else is okay, right? I can hit my intermediate, and the other thing, the energy gaps are way lower, right? But I can't hit any of these lower gaps until I hit that big energy of activation. So that big jump is what I call the rate limiting step. If I don't hit that, I don't have a rate because it doesn't work. So that's like the gatekeeper to the rest of the reaction.
So you need the most energy to hit that step?
Yeah. So a rate limiting step is the step that takes the most energy to get to. That's not necessarily always the first one. Sometimes your second one is your rate limiting step.
Because that would be so you would just circle the first.
Yeah, that would be the rate limiting step. So basically, I have two reactions, two mechanisms going on, right? So my first reaction was taking away the hydrogen. My second reaction was forming the bond. The rate limiting step means that it takes more energy to take off that halogen, right? No, to take off that hydrogen. So that's going to be my rate limiting step. So if we go backwards, this is my rate limiting step. Hold on. That's my rate limiting step. That step takes the most energy. Questions? Comments? Did my pen die? Hold on. Oh wait, that's not dead. Okay, good. Okay.
And that was the one. Which one is this? Where you?
It's the one where I pull off the hydrogen. When I pull off the hydrogen, that's my rate limiting step. It takes the most energy to do that. All right, ready to hit question 3? All right, let's go. Okay, question 3, carbocation stability. All right, so basically there's some rules for carbocations. First things first, here's a pro tip. You can remember cation because you have the T in the middle, that's a plus sign. So that's how you know it's a cation. And I have a little thing for anions as well. But cation, because you have a T in the middle, it's a plus sign.
Or if you're a cat person, it's a positive sign.
Yes, except I like dogs, so I don't agree with that. But if that floats your boat, go ahead. I could see you just waiting to tell me that. All right.
No, I just think of it right now. Okay.
Yeah, I've heard people say that one too, but I like it because you have the little T, so it's a positive sign. Okay, so when we do carbocation stability, do I have extra electrons or lack of electrons? I have a lack of electrons, right? And so when I think through this, resonance is going to be good. So benzylic position is going to be the best. Then allylic position. Then tertiary, secondary, primary, and methyl, and then vinylic.
What is the benzylic one?
Benzylic position is off of benzene. So benzene is this,
Oh.
and the position right next to it is what we call the benzylic position. Okay?
What is the M and B?
Methyl,
Oh,
this is going to be vinylic is on a double bond. So for example, do you see how the positive charge is on that bond?
Mm-hmm.
No, bad, very bad.
Oh, so that's always just the weakest.
Yeah, that's very bad. It's like gross. Don't do that. Especially you're like on a test and you're like, I could pick a allylic position or a vinylic. And you're like, no, don't pick the vinylic. Allylic, way better.
And allylic is just one away.
One away from a double bond.
Would be the opposite side.
Okay, so let me just go ahead and what I like to do when I do these ranking questions is I'm just going to go through and just write down what they are. So this one, what do I have?
Oh, you mean
What kind of carbocation is it? Tertiary, tertiary. Comments? Anybody agree? Disagree?
this has to 3 things.
Yes, this is a tertiary. Here, what do I have?
Secondary.
Secondary.
And also next.
And
And
So this is allylic. I like to call this resonating, so I'm gonna call it that. I'm going to call this resonating secondary. Okay. Here I have a secondary. Perfect. Here I have a
Benzyl.
benzylic secondary. And here, what do I have?
that's just a methyl.
But I'm next to a benzene.
It's a primary.
Primary.
But there's a benzene here, so isn't it
Oh.
benzylic?
No,
No, why not?
because it's two.
Because
Yeah.
not next to.
Perfect. People will literally trip you up on that, so good catch, right? Just because I have a benzene somewhere doesn't make it benzylic. This is benzylic. This is not benzylic. Okay? Make sure you're paying attention. Where is your carbocation? It's not benzylic, it's too far away, so this is a primary. Okay. So now I've ranked or here I've labeled what they are, what they do. So, which one is going to be my, let's do,
The fourth one will be the most stable.
okay, 1 equals best here. That would be done. Or, yeah, 1 equals most. Most stable. Most stable. Okay, so 1 is going to be 4.
Then this allylic one.
Let me change the color, hold on. 1, okay,
Then the second one, allylic one, will be the second.
okay,
Then the third degree.
okay.
The secondary.
Do y'all agree with this?
Yes.
Disagree? Yeah. Pretty simple. Do y'all know why the tertiary is better than the primary? There's a term for that. You guys don't need to know it, but I like to kind of explain why it is. Alright, so when I have a tertiary, I have more methyls, right? When I have more methyls, what I get is something called hyperconjugation. What that means is these can all donate electron density towards that carbocation, helping stabilize it, right? Because carbocations are more electrons or less?
Less.
Less, right? I'm lacking electrons. And so the methyls I have right next to me can help donate those electrons towards my carbocation. And so the reason why benzylic is better than allylic is because benzylic, I have all these resonance, right? And so that's why benzylic is the best. Questions, comments? Perfect. So the next one we're going to do is anion. So we can think of anion as a negative ion.
Is it the exact opposite of cation?
Yes, except benzylic is going to stay, like, we're going to keep the resonance ones because spreading it out is always better. But I'm going to switch it when it comes to primary, secondary, and tertiary methyl. All right.
So only benzylic, even in this case, will be the most stable, but
Yes.
after that it will be all switched.
Yeah, so it's benzylic, then allylic / resonance, then methyl, then primary, then secondary, then tertiary, then vanillic, right? So everything, it's these 4 that change positions, but the others stay.
Is there a reason?
All right, so let's think about it. Is an anion extra electrons or lack of electrons? Extra. So, if I have, so here I have a tertiary, right? If I have hyperconjugation, I have all these methyls, that are willing to donate electrons towards my extra electron site. Do I like that or dislike that? I have extra electrons, and all my friends are like, here's more electrons.
You don't want that.
I don't want that, right? I want to be in a place where I don't have all these electrons going on. So, tertiary is worst. Whereas primary, I have extra electrons, and there's only one thing that's giving it to me, and so I'm happier. But the reason why resonance is so much better is because it's a way I can spread those extra electrons around. Actually, guys, when we think about carboanions, carbanion, I don't know how to say that. Okay, anyway, I just realized that there's no O, so it's not carboanion. Yikes. Alright, anyway, so the negative charge is very similar to the way we rank acids, right? Because acids, we pull off the hydrogen and we get the negative charge. So it's very similar. Alright, so let's just go through and say what these are. So here I have a what position? Benzylic primary. Here I have a
Tertiary.
tertiary. Here I have a
Primary.
primary,
Secondary.
secondary,
This is
Both benzylic and vanilla.
but it cannot be benzylic because the double bond is right next to it. So it's not technically right next to it.
it would be, okay, yes, it's kind of benzylic and vanillic, but it's going to be vanillic in this case because it's directly on the bond.
Okay.
So, it's kind of weird, but it's going to be vanillic. Alright, so let's rank them, starting with 5 equals most stable. Alright, so which one is the most stable? First one, right, for the bromine position. And what's the second most stable?
Primary.
Primary, perfect. Third most stable?
Secondary.
Secondary. Fourth most stable?
Tertiary.
Tertiary. And least stable of all, vanillic. Sad face.
So one is the most stable, not the
What is most stable?
you wrote 5 is most.
Sorry. What is most stable? Alright, does this make sense? Questions, comments? Alright, perfect. Alright, now let's do speed of bromination. So, if I'm thinking through speed of bromination, what am I thinking through?
Like it's selective, so you need to think through the position of which it's gonna make the bond.
Yes. So the main thing I'm going to think about when I talk about speed of bromination, when I'm dealing with these, is I'm going to think most stable radical. Right? Because my rate limiting step is what? The formation of the radical. So if I have a more stable radical position, I'm going to have a faster rate limiting step. And if my rate limiting step is lower energy, my reaction is going to go fast. So, for the first structure, where do I want to put my radical? Here?
Yes.
So what I get here, if I resonate, is I get 2 primaries, right? This is what we're going to call resonating primary. Oh, by the way, the ranking for this is going to be same as carbocation. So, benzylic, better than allylic, better than tertiary, secondary, primary, methyl, vanillic. Same rules. Alright. So here I have a resonating. Here, what do I have?
It's a benzylic.
I put a radical there, but it is benzylic, because look. So this is actually benzylic. This is going to be benzylic secondary / primary, right? Because I get primary and a secondary and it's benzylic. So just thinking ahead, right? We don't have to rank just yet, but am I thinking this is good or bad?
That's good.
Pretty good. This is actually pretty dang good. Not only am I in the benzylic position, I'm also resonating, right? So not only do I have resonance within my benzene, I get all this extra resonance too. This is really good.
This is definitely one.
Yes, this is most likely one. I don't know. Maybe someone decides something that's even better, but this is pretty good. So here I get three. I get a primary position and a secondary position. We don't know which secondary position it's going to pick, but we know it's going to favor a secondary position. So we're going to just call it secondary. We're not quite sure which one it is, but we know it's a secondary. Okay. The next one, I can put it here or here. Now, if I put it here, I get a primary, tertiary. If I get here, I get a secondary, secondary. Either way,
What
I
do you
get-
mean by primary / tertiary?
because
It's only attached to the
Because it can
one.
resonate.
because it can resonate. So if I do it that way, I can get this.
Okay.
Let me redraw that. Do you want me to draw it out, or does that make sense?
Yes.
All right, let me. Do you guys want me to draw it out? Yes.
So it's
Yeah.
resonating, right? The
Yeah.
double
So
bonds
it can resonate like this or resonate like this.
So if it resonates that way, that radical will move on to the carbon that's
Okay, here. Let me draw it out. Okay, so let me call. Okay, so this one is going to be purple. And this is going to be tertiary primary. Basically what I have is this,
Mhm.
and then the secondary is going to be orange. And what's going to happen with that is secondary. What's going to happen is I get secondary versus primary, tertiary. All right, so here I'm going to put. Hold on. I'm going to put resonating. Okay? And then here I get
Tertiary.
tertiary. Okay. So, let's go ahead and start ranking. So, what's going to be my first one?
The benzylic.
Benzylic. Perfect. What's going to be my second one?
Resonance comes second.
Okay, I have two resonating structures. Which one do I like more?
the top one, the tertiary.
Tertiary.
Well, I'm choosing between two structures. I'm going to be really honest. Choosing between a tertiary primary versus a secondary is very, very hard. However, our jobs are easy. I can pick between a tertiary primary / secondary or a primary. Which one do I like?
Or
The fourth. Does that make sense?
Yes.
So, choosing between either this resonance structure or this resonance structure is going to be kind of hard. I'll be honest, there could be good arguments for both. Personally, I would pick the purple one, primary, tertiary, but they're all pretty close. But overall, between the first one and the fourth one wins. Because even if I have a primary, I get tertiary primary versus primary. But still, resonance beats the others. And then I have tertiary
Fourth and then last.
and fifth. Oh, one equals most stable. Alright, does this make sense?
Mhm.
Question, comment?